Okay, so this is the part 3 of lecture 4. And I'm going to talk about electrons around the model we're using this semester of the atom, the Bohr model, and how they are involved in explaining the reactivity, particularly for becoming ions. So let's go to the slides. So here's where I left off. Well, that's where I left off. And where elements are on the periodic table will tell you about its reactivity, particularly its potential to become an ion. And this has to do with where the electrons are in the orbit. Now, I went into pretty good detail with this in the lecture. Obviously, this is not pre-recorded. So if you need more, go to your link of the recorded live lecture to see if that helps fill in the gaps. So going down in columns, we call that the group. Cross rows is the period. Remember, hydrogen acts like a non-metal over here, but she's over here because she has one proton. The goal of any element is to get to its lowest energy level. Energy levels drive chemistry. They drive everything, which is this, the noble gases. These are your halogens here. So these are the noble gases, and we call it the noble gas state or the noble gas configuration, which means an element has the same number of electrons as the nearest noble gas. So chlorine, if chlorine adds one electron, it has the argon configuration. It has the same number of electrons as argon, and it's an ion. If magnesium or sodium lose either 2 electrons or 1 electron, magnesium loses 2, it goes 1, 2. If sodium loses 1, it goes over here. They both go to the neon electron configuration. This is the period behind it because it's the next one in. So if it loses the electrons in the outer shell, the paired electrons are the ones that are in the next inner shell. And then, of course, they're already paired because they have to be paired before we went to period 3 to start adding electrons for sodium, for magnesium, for aluminum, etc. So I'm going to go over the Bohr model, how these are added and how we show them. In 1869, Mendeleev published the first periodic table, which was an arrangement of elements by mass. And this is pretty amazing when you think about the limited amount of instrumentation that was available to them. And yet not only did he create, and this was actually the first periodic table, it was developed into the actual table form shortly after, and we still use that. It's just amazing how good they were, how much they got it right so long ago. But not only did he calculate, figure out, determine, identify the masses of these elements that were known, he also realized that there were some unknown elements that were going to have these specific masses. And so he left spaces for them, which is pretty amazing. And so that was 1869, and we're still using his determinations today with a few little upgrades. So you have families and groups, or group, we call the columns groups. I guess sometimes you can see them family, but we call them groups. There are 2 different designations you'll see on the periodic table going across the top. This one has the more modern 1 through 18, continuous. But the way I learned, and honestly the way most chemists use, is the Roman numeral 1 through 8 and a letter A or B. It's broken up. So there's a history behind that, but just be aware that there are 2 different ways. They're both accurate. And that's how we designate the groups. So here's the one with, this is the one I'm familiar with, 1, 2, 1A, 2A, 3A, etc. And then in parentheses below, you see the continuous numbering. So you can use either. So the main ones that we're going to work with are A, the transitions are B. But we use this to identify the group. So if I say something is in group 5A or 15, and period 3, you can look that up as an address and say, oh, that's phosphorus, right? Here's period 3. Now, most periodic tables do not have the period numbers written in. So you can write them yourself or count them. Remember to start at hydrogen. But you go across period 3 to group 15 or 5A, and that's an address for phosphorus. This is also, the period corresponds to the shell or the orbit that's holding the electrons for that particular element. So phosphorus is in the third shell out from the nucleus, or the third orbit in the model we're using this semester. As we go across, one step at a time, one element at a time. Now notice we skip the transition space here, so you're just going from sodium, magnesium, straight to aluminum. You increase with the number of proteins. One protein adds with each step over of an element. And the number of protons. The number of protons never changes for an element. Sodium will always have 11 protons. It might not always have 11 electrons, obviously. Okay, it becomes an ion easily. And it may not always have the same number of neutrons, but it will always have the same number of protons. And as we go across, you jump that gap there, you are increasing by 1 proton, which means the positive charge is getting increasingly dense. It's getting stronger and stronger because your size, you're not adding orbits. So you're adding electrons, you're adding protons, and so it's pulling the radius of the element in. You get to your noble gas, you have a filled shell, and we start all over again with the next period, which is the next outer shell. All right, so we're using, we studied the atomic theories up to, the discovery of, did we do the nucleus? Right. So we talked about Rutherford's with the alpha particles and discovering the nucleus, and then the protons were concentrated in there. And then that was 1909. So only 4 years later, really, very quickly. So they're working on all this all at the same time. Came Bohr's model of the planetary model, which says the electrons are circling around the nucleus in specific fixed orbits, just like our planets around the sun. They're not randomly placed in there. They're not just whirling around wherever. They actually have specific set orbits that they travel in. And until the nuclear model, quantum mechanical model that we use now, that was the model used. And so, by the way, I talked about, so there's Rutherford's nucleus. So Bohr's, look at all this happened right around in the same period of years, very close in time. Then in the 1920s, we start coming up with the quantum mechanical model. So there was a lot happening in chemistry right around this time. And then the neutron was discovered and determined in 1932. All right, let's look at the Bohr's model. One of the important things about the Bohr model is the fact that it establishes not only specific orbits for the electron to be in, but since it can only exist in those specific orbits, so this is the foundation of the quantum mechanical model. When an atom absorbs energy, so your electrons absorb energy from light, usually a laser, radiation, all kinds of, so it's energy, it's radiation, it's wavelengths of energy. It jumps up, it's excited, it absorbs that energy and it jumps up to a higher orbit. Now there are infinite number of orbits that it can go to. And later in Chem 1, we'll talk about orbitals when we do this. So infinite number. So it's excited up, but it's a specific set energy portion that it goes to. It can't just randomly jump anywhere. And then it has to get rid of that energy. It has to relax back home. And it can either do that all at once, or it can do it stepwise. Jump down a few, jump down a few. And it does all of those. Remember, you have a lot of electrons in an atom. And so it's not just the valence ones that can be excited. They can all be excited. So the pattern of excitation and emission. Emission is when the electron relaxes, it has to get rid of that energy. It emits it. And so that is an energy that can be measured. And some of it is in the visible wavelength. When that happens, we get a specific spectra of those electrons relaxing back down to their starting place, get all different spectra because they're coming from different locations and they're ending up back at different locations, different orbits. And every element has a very specific pattern of this emission that acts like a fingerprint. So you can identify any element by exciting it and looking at its emission fingerprint. And it's not always just in visible. Generally, you look at the ultraviolet, the visible, and the IR, UV, and vis. Infrared, ultraviolet, and visible. Okay, so this was the foundation for quantum chemistry, because quantum means packet. It means a set amount. And so that's describing this packet of energy that's absorbed to jump to a specific different orbit and then released to come back down. And that's where the term quantum comes from. So let's look at Bohr's model. We have a core with a proton, and we have the first area that electrons reside in. We call that the first shell or the first orbit. Now, the very first one only has 2 electrons. And if you look at the periodic table, you have hydrogen and helium just up there by themselves. That's your first shell or your first orbit. It has 2 electrons. It's the tiniest one. There's not any more space for any other electrons right there, because electrons repel each other. So they've got to be far enough away from each other. And it's just a space issue. Okay. Because they're attracted to the proton charge, but they're also, they repel each other. Because you still have, even though they have different spins, you still have 2 negative charges here. And so it's that combination of the repulsion and the attraction. So they get as close as they can to the protons, but they can't get too close because then they're too close to each other. And you have a perfect distance, and that determines the distance from the nucleus and the size of the orbit. All right, so now the next orbit, the next period, the next shell, so we're down to period 2, has space for more electrons. And there, as you go from left to right on the periodic table, you're adding 1 electron at a time. So here's lithium. This outer ring is called the valence electrons. So the current period that the element is in, those electrons are called valence. They are the ones that are available for chemical reactions. And you add electrons until you have a total of 8 in the shell. The only one, the inner one only has 2 because that's all it has room for, but all of the other ones that we're going to use have 8. 8 electrons is 4 pairs. That's considered a filled shell. There's no more room for any. That that element is at its lowest energy level at that point. It's happy, it's content, it's the least reactive because it does not want to give up or take any more electrons. It's perfect. So that's the goal of every element, is to get to that noble gas configuration or the one behind it. For lithium, it's much easier to lose one electron, and then it will have this electron configuration. So the lithium will actually end up with the configuration of the period behind it, because it's just easier for it to lose one electron than to gain 7 more. Because every time you gain or lose an electron, there's an exchange of energy. Sometimes it requires energy, sometimes it releases energy, but energy is involved. And if you're adding and you're adding and you're adding and it's getting crowded, you're going to be requiring energy. So whether it gives up an electron or takes it, depending on where it is in the periodic table. And remember, if it gives up an electron, you now have an imbalance. So lithium, you would have 3 protons, but only 2 electrons when it has this configuration. So it would have that's why lithium has a +1 charge as an ion. Lithium is a +1 cation. So here are some examples. So this is what the model you'll be using in this class to display the electrons around the nucleus in the orbits. First period, there are only 2, so there's only room. And for the first one, it doesn't matter if you put the 2 like this or separate. They are opposite spins, so it just doesn't matter. However, all the rest, it does matter. So we're at the second period, so the second shell or the second orbit. Notice that the 4 electrons are placed at like the o'clock positions, 1, 1, 1, 1. You have to do it because of the spin. They all have the same spin, which term you'll learn about later. You're paired. The only way for an electrons to exist as a pair, to share the same space, is if they have opposite spins. And it's just, we draw up and down arrows to designate the spin. So the first set all have the same spin. And so when we fill the second spin, that's the opposite spin. So you go 1, 2, 3, 4, and then 5, 6. This is fluorine, 7. Now notice fluorine only needs 1 more electron to get to this perfect paired state. And so that's why fluorine exists, if it's an ion, as a -1 anion, because it takes that 1 ion, any chance it gets, that 1 electron, to get a filled shell, noble gas configuration, and that gives it a 1- charge. So that's why fluorine ions are -1 charge. Lithium ions are +1 charge because it's easier for them to get rid of that. Carbon depends on the circumstances. We go to period 3. So we have three shells, 3 orbits. There's the first one, it only has 2. There's the second, there's your 8, your third. So sodium has 1 electron. It's easier for sodium to get rid of that 1 electron. It will then have the noble gas configuration of the neon, which is the period behind it, and it's happy. So sodium travels as a +1 cation, and that's why. So there's silicon, chlorine. Chlorine, once again, just like fluorine, we have 7 electrons, valence electrons. This is always about the valence electrons. So it requires 1 more to get to the perfect argon configuration of everything paired. And so if you notice, fluorine and chlorine each only need 1 electron. And so they take that. And so as you would imagine, they have similar chemical characteristics because of that. Lithium and sodium have similar chemical characteristics because a lot of their chemical reactivity involves the loss of that 1 electron. So where does fluorine get her electron from? If it's becoming an ion, it gets it from another element who's giving the electron away. So it's an immediate exchange to get to that lower energy level. So that's why these elements become atoms. I mean ions, I apologize. And why they become the ions that they do. So, all right, so we have a model here. Which atom is this? You should be able to tell this. Because it's not an ion, the number of electrons is going to equal the number of protons. So you can either just count the number of electrons, because there aren't that many, so it's not too hard. So 2, 4, 5, 6, 7. And you can go back and look at your periodic table. And the element with the number 7, which would also be the number of protons, is nitrogen. But the other thing is, and it's important you know how to do this, is looking at location. So we have 2 orbits or 2 shells, so I know it's at period 2. And it has 1, 2, 3, 4, 5 electrons, so it's going to be 5 spaces over. Because remember, every time you go over 1 space, you add an electron. It's not an ion. We weren't told it was an ion, so therefore we can go with those theories. And so if we go back to the periodic table and we go to period 2, here you go, and count 5 spaces over. So 1, 2, 3, 4, 5, and there we are. There's the nitrogen. If you have only a few electrons, it's easy to count, but if you end up with, a lot more like this one, that's too many. I'm just going to go with the simpler way of saying, look at the address. There are 3 shells or 3 orbits, so it's going to be in period 3. And there are 2 electrons, so it's going to be 2 spaces over. So let's go back to the periodic table. Here's period 3, and we go 1, 2 electrons, so that is magnesium, and that's why we identify them. And if you want to go back and count, you will find 12 electrons there, because magnesium has 12 protons, and since this is not an ion, it also has 12 electrons, and so your answer is B. Now, very important to remember that all of these electrons that we're talking about moving around, losing, gaining, are valence electrons. So if you're asked a question, how many valence electrons does something have? Only look at where it is in the periodic table, which group number. It's not asking for how many total, which goes back to all of the previous shells. You're only looking at the outside shell. If I ask you how many valence electrons does magnesium ion have, the answer is 0. Because the shell is still there, all right? Period 3, the shell for period 3 is still there. There's nothing in it. It gave up the 2 electrons to become an ion, but it's still there. So the valence electrons are 0. Yes, it has these, but these are not valence electrons. The valence are the ones that correspond to the period or shell number or orbit number that the element is in. So this is, again, why elements gain and lose electrons to become ions, and why noble gases are not reactive, or pretty much, we pretty much call them not reactive, non-reactive, because your noble gases, they're not going to gain or lose electrons. They're happy. They're all paired. They're at the lowest energy state. They're done. Go away. We don't want any. We're not giving you any. And so that's the noble gas configuration that all of the elements are striving to become. When you have shared electrons, by the practice of sharing, that exchange, that sharing of electrons still gives them the noble gas configuration. Because the electron that, let's say, 2 fluorines are sharing, each one is sharing that extra one of the other. The use of it counts as the extra electron. Okay, this is just another illustration that some people find helpful. It's a periodic table wrapped around, but it's slightly off. So it's showing the noble gas configuration and each element next to the configuration that it is striving to be like. So here are the ions, here's the configuration, here are the cations, and here's the corresponding configuration. But notice sodium is in period 3, but the neon is period 2. So be careful. The cations, when they lose the electrons, they get the configuration of the noble gas in the period behind it. It's the inner orbit that's filled, that they're accessing. But so their valences are 0, their valence electrons are 8. So be careful with that. Just a recap of ions. If it's an anion, we add the IDE, just like in a naming of a compound. But if it's a cation, we just say the name of it, and then we say ion or cation. So potassium, and you can look at your periodic table as I go through these. Where is potassium? So I'm just going to verbally do it, but you can look at your periodic table as I go through these. Potassium is in group 1, period 4, but it actually doesn't matter that it's in period 4. The fact that it's in group 1, it's going to lose 1 electron. It's the easiest thing to do. Therefore, potassium will have a +1 charge because it's going to lose 1 electron. So that will be A. Aluminum is over in group 3A. Now I'm using the AB naming. So it's easier for aluminum to lose 3 electrons than to gain 5. And therefore, aluminum will lose those 3 electrons, and it has a 3+ charge. Phosphorus is over at 5A. For phosphorus, it's easier for it to gain 1, 2, 3. All right, that's not one of our choices. 1, 2, 3. Well, -3 is not on here for some reason because phosphorus would gain 3 electrons. So go to chlorine. Chlorine is a halogen. It is at 7A. It is right next to the noble gases. It needs 1 more electron to get to that configuration. So it's going to take it. So when it adds an electron, it's going to have a -1 charge. It now has 1 more electron than protons. Oxygen is 6A. When I talk about 6A, 8A is the group number for the noble gases. So if you find oxygen, it's at period 2, group 6A. It is only 2 places away from the noble gas. So it only needs 2 electrons to get that fully paired configuration. And so oxygen will travel as a -2 anion, D. Nitrogen is next to it on the other way. So it needs 3 electrons to become, and again, -3 is not on here. I don't know why. But nitrogen will be -3 anion. Calcium is all the way back over to group 2. Group 2A, it's easier then to lose electrons than to gain, because it can lose 2 or it can gain 6. So it's going to lose the 2, and therefore it has 2 fewer electrons than protons, and calcium is going to have a +2 charge. Lithium is the second period in group 1A, just like potassium. Potassium's a little further down, but everything in group 1A is going to lose 1 electron and have a +1 charge. Iron can have multiple charges. So you don't predict iron, you memorize iron. So I'll let you go back to your, iron is here, right? There's iron. So iron can have either a +2 or a +3 charge, which is why when we are naming a compound with iron in it, we put iron in Roman numerals to indicate which of these it is. So in this case, this says it's an ion. Language is very important here. So you know that the number of electrons and the number of protons are not going to be the same. Now, the fact that there are 9 protons, right there you can go to the periodic table and say, all right, which one has 9 protons? And it's fluorine. But let's double check, because what does fluorine travel as? It travels as a -1 when it has its full shell. Another way you can look at this, it's an ion. It has 9 protons. It has 10 total electrons, 8 valence, 2 inner shell. So it has 10 electrons, 9 protons, so it's going to have a -1 charge. And of course, that's the only one in our pick choice here, in our selection of that has a -1 charge. So even if you didn't know this was fluorine, you would know that it has a -1 charge, and that's the only one here that has a -1. This one has a -2. So a couple of ways to answer this question. This is an atom, and the question is asking is what will be the charge when it becomes an ion? Well, it has 3 shells. That actually doesn't even matter, but it has 3 valence electrons. So it will be easier for it to lose these 3 electrons than to gain 5 to get to the filled shell status, all paired electrons. So it's going to lose these 3. It's going to have a +3 charge, or 3+. And as a result, when it becomes an ion, the valence shells will be 0, and it will have the noble gas configuration of the prior noble gas. So if this is period 3, and it has 3 electrons, that's aluminum, right? 1, 2, 3. And by the way, make sure you start, if you count, you start from the outside. If you go from here, you'll count wrong. 1, 2, 3, and go over. So that's aluminum. But when aluminum loses its electrons, the electron configuration that it's going to carry now is neon, which is the period 2, because it's getting rid of the outer core and it's going to be the configuration of the inner core. So again, just think of the process of what's happening. Really, electron configuration, electron placement is, it's logic, it's understanding, it's not memorization. And really, that's it for this part of the lecture. I did go into more detail in the live recording, so if you still need more, go ahead and go back to that and have it, to fill in the gaps.